All right, welcome back. Good. So we introduced the vectors now. We talked about scalar multiplication that allows us to change the length of the vector or the opposite direction. We talked about addition of vectors that allows us to create new vectors that point in a different direction. So the question now is, of course, when we want to use vectors to create objects, what kind of vectors can we create with these two operations? Or the other way around, if we want to create a particular vector, what kind of operations do we need, and how many numbers of vectors do we need to create this new kind of vector? And it's clear, for example, that scalar multiplication as an operation is not enough because it doesn't allow us to change. It only allows us to change the length, but not the direction. Also, adding parallel vectors will not be enough because by adding a parallel vector to another one, we also don't change the direction because that's how parallelism is defined. So to create a new vector that is pointing in another direction, what we need is to add at least two non-parallel vectors. And it actually turns out that this is enough in 2D, that we just need two vectors to create any random vector in 2D. And this is intuitively clear. I mean, so far I already basically used this and no one really complained because I think it was really intuitively clear to you that I said, okay, we have this index here, 0, 0, 0. And then we have one direction, which we often call the x direction, and we have another direction, which we call the y direction, and then we have like a unit here that we say, okay, this is, for example, 1, 0, and this is 0, 1. And because of how I started with this, with the pixel image, the raster display, it was basically intuitively clear for everyone that by using these two values in these two directions, we can describe every point in space. And this is now the formal definition of it. If we have two vectors that are nonlinear, that are linearly independent, which means that they are not parallel, then we say they form a 2D basis, so they allow us to build any new vector in our 2D space just by making a weighted addition of these two vectors. So using scalar multiplication and addition, we can create any new random vector in our 2D space. And you see here now this definition does not say anything about the angle between the vectors. It just says it has to be linearly independent. So it just has to be two non-parallel vectors because, like I just said, if you want to create a new vector with two parallel ones, you cannot create a vector pointing in a random direction. So you need to have, they need to be non-parallel, but they not necessarily need to be in the right angle. They could also be something like this here. And then if you have a unit here, you basically get a grid that is a little shifted, but you can address each point within this grid in a unique way, in a similar way as you can do it with here, with this grid based on this right angle. And of course, this right angle is much more intuitive to us, usually, especially when you introduce it like I did with this raster image. But we will see later that there are situations where such a twisted grid, where we have a basis that is not based on two perpendicular vectors, but on two vectors that are just not parallel, so where the angle between the two vectors is just something else than 0 or 180, that this is also possible. And we'll see situation actually next week already, I think, where this is actually where you will realize why this sometimes makes sense to define our coordinate system in that way, because it makes the calculation easier. Good. So we say if we have these two vectors, we call them a basis. And of course, like I said, having them as in a right angle is kind of intuitive. So this is a very special case, and we have we have the special situation if they are orthogonal or perpendicular to each other, and then we have an even more special case if they are also unit vectors, because then we define them as a so-called orthonormal basis. So we have perpendicular vectors that have an angle of 90 degrees, they are perpendicular to each other, then we say they are orthogonal to each other and they form an orthonormal basis. And this is comes in quite handy, first of all, because it is our intuition very often that we think about this. And also it's very useful for calculation, as we will see later in the course, and you will see in the practicals probably. Then, for example, if you think about the length of the vector, the Pythagoras, if we have a vector here, vector v, and then we have here v1, v1, v2, then you see if we calculate the length based on this one here, then this description of this vector, we can describe this vector as v is v1 times x plus v2 times y, and then we get this vector. So we really see here that this is very easy to describe. Good, and this is called then the Cartesian coordinate system that I mentioned earlier. This here, this so good, yeah. So we said we have a vector with a length and a direction. We can manipulate by scalar multiplication and addition, and that allows us to create any random vector. So this is basically all we need, but of course there are other operations that we do not necessarily need to create a new vector, but they can be very useful, can have very useful characteristics depending on how we define them, of course, for example. And the first example is the so-called dot product or inner product or scalar product. Don't confuse scalar product with scalar multiplication. It's called scalar product because the end of it is a scalar. But we do not multiply a scalar with a vector, but we multiply two vectors with each other, and the result is a scalar. And we do this by this definition. The scalar product of a vector v and w is the product of each coordinate of the corresponding coordinates with each other, and then taking the sum over all coordinates. And then you see, of course, the result is a single value. So a single value is, of course, not interesting in terms of creating new objects or creating new things, but it has certain characteristics that come in quite handy and that are very useful in graphics, because we have this relation between the scalar product and the angle between the two vectors. So this theta here is the angle between the two vectors. If we have vector v and a vector w, then theta is the angle between them. And for the scalar product, there is this condition that the scalar product divided by the product of the lengths of these two vectors is the same as the cosine of the angle between the two vectors. In the book, they actually use this as a definition and then show that for the Cartesian coordinate system, that the equation that I used to define it is actually correct. So if you want to know how to get from the equation to here, you can also look at the book and then just go the other way. But I will not go into the details here, but I will describe now why this is very useful for us in graphics, why this characteristic is very useful for us. So first let's repeat the cosine function. I hope that at least most of you know this from school, how the cosine looks like. So the cosine is a function that starts here at 1, and goes down to 1, and then goes up again for like 360 degree. Here we have 180 degree. Here we have 0, of course. Here we have 90 degree, and here we have 270 degree. So so we see based on this that the scalar product is maximum at a cosine of 0 and at a cosine of 180 degree, and 360 degree is then again the same as 0 because that's one way around the circle, of course. So we see the scalar product is maximum if they are pointing in the same direction, because then the cosine the theta is 0, or if the theta is 180 degree, which means they are pointing in directly opposite direction. So then the scalar product is maximum, and it gets and it is minimum for the right angle. The right angle or 270 degree. So a right angle here. So we see that the scalar product, the dot product, gives us an indication about how the vectors are, how far they are pointing away from each other, informally speaking. And that is something that comes in quite handy sometimes. But it is also very useful in graphics because it gives us an easy way to calculate the angle between two given vectors. And this is something that we need very often, for example, when we want to do light calculation. Because, for example, if you have a surface and the light comes in here, and we model this light by a vector, then the intensity, how much this light is reflected, depends on the angle with which it hits the surface. So if it hits directly, the reflection is stronger than if it just hits from the side. We will talk about this later. But just as an example that you see, if we model the surface with the vector and if we model the light with the vector, you can easily imagine why it is important in graphics that we know how to get the angle and that we have a method to get the angle very easily. And the dot product is exactly doing that. Good. Yeah, so these are just a couple of things that you can also do for yourself as an exercise. I think I will probably skip them also to save a little time here. So it's always good when you learn something new that you think about some special cases. So for example, what is the inner product of a unit vector with itself, or what do you know if the dot product of two vectors is 0? Of course, think about the condition that we had, that the cosine of theta, the dot product of two vectors is the cosine of theta times with the length of w. So you see, if that is 0, there are basically three options. Vector of w, v or w are the null vector, or the cosine is 0. If you look at the cosine function, you see that this means that they have a right angle. Good. And for a unit vector, you can figure it out yourself. Good. Another thing that often is quite useful, where we can another way where I can use the dot product that is often quite useful is to calculate the projection of the vector onto another one. So if you have a vector, let's call it v, and a vector, so annoying, a vector w, then the projection is defined as the length p here, if we project this vector down here. So this is not the vector, this is a scalar value, just the distance here. And if you think about what we had here, this vw is the length of v times the length of w times cosine theta. And if you think about trigonometry, we have here this angle theta, we have here the right angle, then we know that the cosine of theta is defined as p divided by the length of this vector, which is this side here. And if we put this in here, then we see that v divided the scalar product divided by the length of this vector w is exactly this scalar value p. And if you don't know now why this comes in quite handy in graphics, I will recommend that you do the practicals. Then you will know, hopefully. Good. Yeah, so this is the dot product, scalar product. Of course, there are other ways to define multiplication with vectors, and one interesting and one very useful way to do this, to do multiplication of vectors in graphics, is the so-called cross product. Again, we multiply two vectors with each other, but in contrast to the dot product, the result of this multiplication is another vector. And you see here it is defined by this rather weird looking formula, which is indeed not as like symmetric or intuitive as the dot product. But the interesting thing is, of course, the characteristic of the vector that comes out of this vector multiplication, of this cross product here. There is also a relation with trigonometry, which is then not the cosine but the sine. But be aware that this here is only a characteristic, so we can have here the length of this resulting vector is calculated by the length of this individual vector times the sign of theta. So this is just a characteristic. This cannot be used to define it, of course, because it doesn't even appear in here, only with the scalar value, the length. But it is something that comes in quite handy. And so this definition looks a little strange, but it has a very, very useful characteristic, which is that the resulting vector is orthogonal to the original ones. So if we have a vector v and a vector w, and then we build a cross product of these two vectors, we get a vector that is orthogonal to the vector v and orthogonal to the vector w. And this is, of course, very interesting in graphics, because very often we have a situation that we want to create an orthogonal vector. And so the question now is, why is this the case? Can we prove that? And of course, how could we prove that? Of course, we already said that if you think about when we mentioned orthogonal today, it was mentioned in relation to the cross product, that we said the cross product, if the cross product is if an angle between two vectors is 90 degrees, then the cross product is 0, because the cross product depends on the cosine of this vector, and the cosine of 90 degrees is 0. So if we show that the cross product of the vector v with if we show that the dot product with the cross product v and w of v and w individually is 0, then we have proved that it is orthogonal. Okay, that was stupid sentence. Sorry for that. I give you the proof, and then you'll see. So what we have to prove is that the scalar product, the scalar product of v and with the cross product of v and w is 0, because if that is 0, then we know that the angle is 90 degrees or 270 degrees, so we know they are orthogonal. And we do this by just taking this definition here and plug in the values. And let me just write it down. I have it here, so I don't make any mistake with the indices. So this is the first one we get. This value here times v minus v1, v3, w2 plus v2, v3, w1. So I may make here two steps in one. I make this cross product, and then I immediately multiply this v1 to these two coefficients, v2 to these two coefficients, because that's how the scalar product is defined. And then we have here minus v2, v1, w3 plus v3, v1, w2 minus v3, v2, v1. And now you see here, this looks pretty much the same here. We can change the order here because, it is commutative. And I purposely wrote this on top of each other, so you see here each of these here removed, gets away, and then the result is 0. So we know indeed that this is orthogonal. And B, then we have to prove, of course, also that it is orthogonal to the other two vectors, and this is something that you can do at home as an exercise, and I really recommend that you do that. Even if you look at this, of course, it is straightforward. It's just taking the formula and plugging the values in, but it shows that this gives you some sort of feeling for it and makes it easier. And this is also an example for how you can prove a lot of statements in a general way by just taking the general form of the vector and then basically writing it out and do some arithmetic transformation until you end up with the situation that you want to prove. I say this because it's a common mistake in exams. I often see that people just take a few examples and then they say, okay, if I take this and that, and then you see this comes out, so they must be orthogonal. But if they just show it with a few examples, they haven't proven the general case. If you want to prove a general case, you have to do it like that. Good. So, then we have so if we have two vectors, we can create a vector that is orthogonal to them. If they are unit vectors, then we have again a special situation, and we can first, the reason why we do this, we can use the cross product to create an orthonormal basis, and that is useful for calculations because the base vectors have the length 1 and are orthogonal, and that is often needed in graphics. So for example, if we have a 3D virtual world that is modeled with a coordinate system, which is sometimes called the world coordinate system or the world system, and we want to model this with respect to a specific camera position, then it might make sense to calculate also from the camera perspective. So we have to create a different coordinate system when we place the camera at a specific position. And this is why we need to create a basis with 3 orthogonal vectors, and the cross product is a way to do that. And if we use unit vectors to create our third vector, then the third vector will also have the length 1, and this is this special thing that I want to mention here. And the reason for this is basically this sign relation that we had here. Because if you look at at the sine function, so I'm also drawing this here to repeat a little bit this trigonometry basics, because I'm not sure how familiar you are with this. I don't want to repeat everything because that would bore a lot of people, but of course I'm also would assume that a lot of people don't remember all this, so I kind of use this indirectly to introduce them also. So this is how the sine function looks like. Again, 1 and -1. I think I forgot to write that down for the cosine. Now if you see the sine of 90 degrees is 1. If we have unit vectors, this means also the length of v and the length of w is 1, and that means, based on that formula here, also the length of the cross product is 1. So this is a very easy way to get an orthonormal basis. Good. So what we do is we have a vector here, and we have another vector here. They are unit vectors, and then we create a vector that has a right angle to both of them, and then we have our orthonormal basis. Now, I have drawn this vector up, but I could have also drawn this vector down, because this is also a right angle. So it is not clear which one it is. And if you plug the values in and calculate v cross w, and if you do the same with w cross v, you will see that you end here up and this is again, doing this transformation is an exercise that I highly recommend. So you see this vector pointing up or pointing down depends on which vector you multiply with which one first. So the order matters in the cross product, which basically mean that so that means that the cross product is not commutative. So not x, but this cross product. Good. All right. So yeah. Oh yeah, that should be across. That's more. Okay, so this is annoying. So this is this cross product. Yeah, exactly. Good. Yeah. So question, what is the cross product of a vector with itself? There are two ways to get an answer to this, or two straightforward ways. One is, of course, you can write it down, plug the values into the formula, general case. The other thing is just, no idea. Use the sign and this condition here, because if it's a vector with itself, the angle is 0, so the cross product is, of course, the null vector, because the sine of 0 degree is 0. And what happens if they're parallel? If they are parallel, then the angle is also 0, so you can also say the null vector. But let's look at the other way to solve this question. We can say if they are parallel, then they are defined like this. So the cross product of V and W is lambda V2, V3, minus V3 lambda V2, and so on. And you see here already that this gives 0, so the result is 0, 0, again the null vector. So just to let you show that, to show you that these are two ways how to prove this. You could have also taken this sign condition to prove that. Good. So yeah, so this is something. So we know now we have vectors, and we know how what a coordinate system is. We even know how to create a coordinate system from vectors or from a few vectors. Then there is this special characteristic of a left and right-handed coordinate system. I just put it here, but I will not talk about this because this is something that you can do in the exercises. There is a text description about this, so if you read that, it's pretty straightforward. You should be able to understand it. I will just so I will not talk about this. I will just talk a little bit about the other thing to give you an idea about why these coordinate systems are so important in graphics, and you will see that in the practicals. But that's also why I will talk a little bit about it, that you understand the idea of it. Because in graphics we're dealing with different situations, we're modeling different things, and I already said that, for example, if we want to create a virtual world, then we have to model this in some kind of world coordinates, or we also sometimes call this world space coordinates. So this can be a little confusing. We tried to make the practicals in a way that we use the same terminology as in the lecture, as in the book, although sometimes we stick then more for the practicals with the XNA and DirectX terminology, and in the lecture I stick more with the terminology used in the book. So it can be a little confusing at the beginning, but we try to make it more unified, but that's how it is in graphics. Often they use related terms, want to say the same thing, but don't use always the same terms, so don't get confused about this. But this is also a thing where you just have to get a feeling and understanding for it. So the reason why we're dealing with this coordinate system, why this is very important in graphics, is that we have certain coordinate system that we're dealing with. So for example, if we have a flight simulation, then we can use the world coordinate space would usually be the virtual world that we model, where we are flying around with our airplane, where we want to fly around. But we also have the view of the pilot, which would be then the camera system, because that is the image that you see from the camera that you use for the modeling. And of course, if you have these two different views, then it is intuitively should be clear that at some point you need to make a connection between the virtual world and this in which you're flying around and the position from where you're seeing it. and that's why you need often to make a transition from one coordinate system to the other. Another thing is, for example, an object system. So for example, if you think about this flight simulator example, you can think about you have the virtual world, and then usually in flight simulation games, if you turn around, you turn with the whole airplane, but you could also implement this in a way that you can fly with the airplane, but you can also look around, and then you have a third camera, which is basically, or you have a third coordinate system. You have the world, you have the objects in the plane, which are sometimes modeled with relation to the plane, and you have the pilot who can look around, which is then the camera system. Good. So yeah, you will understand this more hopefully later when you also do the practical. So just why, as a little example or an illustration on why we're talking about this, because I know this lecture and in general a lot of the first 3 lectures are a lot of mathematics, and when I first heard this I was always wondering, okay, why do we do this and why do we need this? So just as a little understanding here. Good. Yeah. Okay, so far we learned about vectors, we learned about operations we can do with them, and we talked about coordinate systems. And now we want to have some objects in our coordinate space, because of course the ultimate goal is that we want to make some cool graphics. So we need some basic objects. So for example, we need triangles to then use these basic objects to create more complex ones, which is then the process of 3D modeling, which I said we will not cover in this lecture, but we will cover, of course, the basic objects, because without basic objects we cannot display anything. So we'll talk a little bit about lines and circles today, and today we'll restrict ourselves to 2D, and then in the next lecture we'll make the step from 2D to 3D. And to do this, to describe this, I will introduce 2 different representations. So this is again an example from like at the very beginning when I said there are these 2 different ways to define vectors, and depending on the situation, one or the other kind of makes more sense, is more intuitive, or is easier to calculate with. In the same way, we have different ways to describe objects. One of them is the implicit representation, the other is the parametric representation. And you might wonder, why do we need 2 ways to describe the very same thing? The answer is simply that in certain situations, certain representations are easier to handle, or easier to, or more intuitive, or easier to process. Good. So let's start with implicit, and let's start the implicit representation. Let's start with a very general case of an implicit curve. So a curve is intuitively said, it's basically just a line that is drawn without lifting the pen. And so you can think of it, for example, in this case, it's a closed line. So you have this shape here. And of course, it is clear from mathematics, if we are in 2D, we cannot describe this with a regular function, because a regular function usually takes in 2D has something like this. You have f of x, y is f of x. So this is how we know functions in 2D. We have a value x, we plug a parameter, we have a function and we plug a parameter in, and then we get another value. So we have 2 values and we can draw those values in the diagram. But that makes it also clear that we cannot do something where we have a unique value and then we get 2 different ways. So with a normal function we cannot describe this, but we can describe it with a construct like this, that we say basically we basically have a 3-dimensional function here, or no, a function from 2D to a scalar. So we basically imagine this as a 3-dimensional space where we have a set, and then you can of course define a function with 2 parameters that gives you one unique set value for each parameter pair. And if we now take the intersection with the xy plane, so if we just say we look at the values where set is 0, depending on how we define this function, we can get exactly this implicit track here, or this implicit curve. And this is also where the name implicit comes from, because we don't have an explicit function where we can put a value in and then get another value out, but we have a function, an implicit formula that indirectly describes the values. So we have to take values and see if they verify if they fulfill this equation, then they are on the curve and we can, for example, draw them. Now this is the very general case. Of course, in practice, in graphics, we often use more simpler shapes because, like I said, with, for example, a very simple shape, which is a triangle, we can model, for example, circles, but we can also use a circle, use an implicit representation of a circle, and an implicit representation of a circle around the origin. Actually, now I realize that this is the wrong image. So this should be a circle, and this should not be here. A circle around the origin can be represented by by an implicit representation in this way. And if you think about this might not look very straightforward or intuitive to you, but if you think about one thing that we already used today, or if you think about what does it mean that a point lies on this circle, it basically means that, so the circle is defined by the center, which in this case is the origin, and by the radius. And what does it mean that a point is, I knew that this would happen, a point is on the circle? It basically means that the length of this vector describing this point is the same as the radius. Now, the length of a vector we learned today is defined as the square root of its coordinates to the power of 2. So if this p is defined as x and y, this is this, and this has to be, and this point is on the circle if the length is the same as the radius. And now I'm pretty sure you can make the connection to this, and this strange formula looks pretty straightforward. So this is indeed the definition of a circle around the origin, but of course you already saw it from this wrong image that I had here. We're also interested, of course, in placing circles anywhere in our space. So, for example, around a random center C. Actually, that should be a vector. So, yeah, I forgot to update the images, but I thought I at least updated the text correctly. So, good thing I'm not doing the exam. Yeah, so if we have it around the center, again, y, then we can use this equation here. Then the implicit equation looks like this. And why does it look like that? That is part of the tutorials. But just to give you a hint, think about, this is where it also comes in the fact that we're dealing with vectors, and a vector is not a location. A vector is just used to describe a location. So this vector here is used to describe the location with respect to this center here. So this vector is basically the same as if we subtract this vector here. So this is the vector C describing the center. This is the vector P describing the point on the center, which has the same length as the radius if it is on the circle, but it is also the same vector as if we go here. So if you look at this, and if you do it with all the points here, you will see that you see that P is on the circle around the center if P minus C is on the circle around the origin. And if you then do it like this, you have the exercise solved. Good. All right, so these are circles, but also, of course, we have other objects. So, for example, we also have lines. We want to do an implicit representation of a line. Now, probably the most common form of a line representation in a coordinate system is the so-called slope-intercept form, where we have a line defined as y is a times x plus b, which basically means if we have, for example, in the right side, we have y is 1/2 x plus 2. So that means here the slope is a is 1/2, which gives the slope of the line, and the intercept is basically this value b here. B is 2 in our case here, and this is basically the interception with the y-axis. And of course, from this here to the implicit representation, which is basically a function f of xy equals 0, is just bringing those values over to the other side, and then we have our implicit representation. And again, this is an example for something that you would say, why would I do this? This doesn't look intuitive to me. But there are situations where an implicit representation of a line is just easier to calculate with, and then you're happy that you have this representation. Good. Now, if this line intersects with the origin, then of course this factor b is 0, because we just have a slope of the line. And then we can also write this in terms of vectors, in terms of the vector n and the vector p. If we take the vector p, x, y, so these are our two coordinates, the x that we verify if they are on the line with this implicit equation, and we have this parameter, the vector n, which encodes the slope, and 1 here. So if you do the vector multiplication here, you will see that n times v is exactly this, leads to this equation that you have here. Again, this is a good exercise to do. So this is just a different way to represent it, but again, this is a way that sometimes is quite handy, of course, but we do not only want to have intersection lines that intersect with the origin, we also want to have lines that do not intersect with the origin. And the idea is basically, and then this formula becomes n times p minus p0 equals 0, and this p0 is basically just this vector here. So it's basically just take the line and move it over here. So it's pretty much the same as you saw with this circle, although for the circle I explained it the other way around. I said we have a circle somewhere at a center C, and then we move it to the origin, and then we prove that the radius is the same for the origin with this new vector p minus c. And here it is basically the same for the implicit equation. It's p minus p0, but this basically means you take the value from here and move it up, and then you have this equation here. So So this is the general form. Of course, how do we get the concrete values? So if we plug this in here, in these values here, and the values for let's call them POX and POY, so the values for this vector PO, and we get this by minus AX minus POX plus Y minus POY equals 0, and we know the implicit representation is minus AX plus Y minus B equals 0, and that means POX equals 0 and POY equals B. So our vector P0 is 0b, and that is exactly this vector, and if you compare it to here, then it is exactly this, describes this distance here, but instead of describing the distance, you have now a vector pointing in that direction. So it's just a different representation, but it helps sometimes. And this vector n here is perpendicular to this. So remember, we have the slope here. A is 1/2. And this vector is minus a, so it points in the other direction and up, and it goes 1 in this direction, which the result is that this is a perpendicular vector, and this is no coincidence, because it is actually true for the first two coefficients of any implicit line representation that this is a vector perpendicular to the line, and this is why we give it, and these kind of vectors are very important, which is why they have a special name. They are called normal vectors. So, and how do we see that, or how, when I claim this, of course I have to kind of also prove this. So the proof of this is assume two random points on the line. So let's say P0, which is x0, y0, and P1, which is then x1, y1. And if they are on the line, then of course also P1 minus P0 is on the line. So if the point P1 and P0 is on the line, then the difference between those is just this vector, and that is then of course directly on the line. Now I said that n equals, let's just call it AB, is perpendicular to this line, when we can say every random vector on the line is perpendicular to it. But since we did not explicitly specify that, but specify them as random vectors on the line, this P1 minus P0 is also a random vector. So we can just say if the scalar product of n times P1 minus P0 is 0. And if you multiply that out, then if you use these values here and these here and write it out, I'm running out of time, so I'm skipping those steps, then you will come to ax1 minus ax0 plus by1 minus by0 plus c minus c. And if you remember the implicit equation of a line, you will see that this is exactly f of P1 minus f of P0, which per definition, because P and 0 are on the line, must be 0, so the difference is also 0. And since P and P1 were random vectors on the line, and this was a random vector on the line, we have proven that n is orthogonal to each random vector on the line, which means it is orthogonal to the line. Good. So these were the implicit representation, and since I'm running out of time, I will talk about the parametric equation next time. So the last couple of questions on the exercise sheet, skip them for today and do them next week. All right, so we see each other again on Tuesday.